Okay, I think yeah, we should start. So it's my pleasure to introduce Dr. Sasaki, Tokio Sasaki, yeah, from And so he will talk about degeneration of cubic 4 with nodes. Okay, yeah, please.
Thank you for the presentation. Sorry, thank you for the introduction. And today I would like to talk about the degeneration of cubic threefolds. And the title might be a little bit confused. I should have used a different kind of title. So I want to say that the kind of smooth degeneration of smooth cubics towards the cubic threefold with nodes. So it's relating the nodes. Okay, not the degeneration of all cubic threefold with nodes. Okay, and this is a kind of survey research towards. Personally, I'm interested in the somewhat kind of irrationality problem of the cubic fourfolds, and of course it should relate to the spectrum and the new rational invariants relating the spectrum. But towards such a kind of goal, these days I'm observing the cubic threefolds with nodes. So today I want to introduce some known results surrounding this research field. Okay. So as an introduction, I want to introduce the plan of today's talk. Okay, so let me assume that X is a smooth cubic threefold in P4, and for the simplicity, I want to consider here only over the C, or generally one may consider the case of the Azure closed field with a characteristic with a character which is not equal to 2. Okay, and a very famous and celebrating result by the Clemens Griffiths or another proof by the Murre is for general choice. In fact, this cubic threefold X is not rational. Okay. And since any smooth cubic is unilateral, it means that there exists a dominant map from the Pm to X. Okay. X gives an example of unilateral but irrational variety. Okay. And in the proof of this famous theorem, the main tools which are used in the proof were the following 3 subjects. The first one is intermediate Jacobian JX, and it quite related to the Ajak cycles and the kernel of the Hodge maps to the Hodge classes. It is defined by, roughly speaking, some half part of the Hodge diamond quotiented by the homology with the Z quotient, okay, and its zeta divisor. Okay. Also, this intermediate Jacobian of the cubic threefolds was connected to the another subject, which is called the fano variety fx of lines on X. So this is a kind of modular space of the lines. Okay. So these 2 subjects are used in the these 2 subjects are used in the Clemens and Griffiths paper, but also another approach by Murre uses a Prym variety. This is a variety associated to the double coupling of the plane quintics. Okay, I will explain later in the definition. So, by generalizing this observation about the smooth cubic threefolds, one of the natural questions is that, in fact, what does happen when X has singularities? Okay. Especially if we can observe some information of the cubic threefold with singularities, we also can construct a kind of theory of the degeneration of smooth xt to a singular x0. Okay. And if, in fact, the cubic threefold with one node is observed in the classical paper by Collino and Murre, and also recently, the case of the multiple nodes was observed by Gwena. Okay, and even in these cases, starting from the cubic threefold X, we obtain a kind of associated sextic curve S, and similarly to the case of the smooth cubic threefolds, we also can define a kind of two-plane quintic curves delta and delta prime. So sextic curve and two-plane quintic curves. Okay, and these S and delta prime are defined for the choice of each node for the case of the multiple nodes. Okay. Then we can consider a kind of, I may say that, generalized because there is a kind of determinacy and indeterminacy problem I will introduce in my talk. Okay, so here there is a kind of generalized Prim variety even for such a kind of quintic curves delta bar and over delta associated to the covering of these curves. Okay, and though we also can define this generalized Prim variety in some cases, we also can consider just a normalization of these nodal curves, delta prime and delta. Okay. Then in Collino, Murre, and Gwena's paper, they have shown that this normalization of the S and delta prime and delta can be identified via the intermediate Jacobian and the Prim varieties. So there are kind of two approaches. First, we take the normalization and apply the usual definition of the Prim varieties, then we obtain this isomorphism. But on the other hand, we also can consider directly from the nodal curves the kind of generalized version of the Prim variety. Okay. So in today's talk, I especially want to focus on this one. The reason
excuse
why,
me. Excuse me. Yes. Could you explain how X gives this sextic curve S?
Yes. So of course, I would like to introduce in my talk later. Since this is just an introduction, I want to just say there are some curves. Okay, S is given by consider the intersection with the tangent cone. And,
oh, I see.
Yes, I will explain.
I see. Then you will also explain this plane
quintic curves. Yes.
Oh, I see.
Exactly next section. Okay.
I see. And anyway, you claim that this Jacobian of this curve is isomorphic to this Prim variety, right?
Prim variety of the normalizations.
I see. Yeah, thank you very much. Thank you.
Okay, so the reason why I want to consider I want to focus on the Prim variety of the nodal curves is that there is more general theory of the degeneration of Prim varieties by the Professor Alexeev, Barkenheg, and Lang. Okay, and this is a very general theory, and there is a result which says that one cycle of the dual graph of the given covering delta prime, so it is denoted by gamma delta prime. Okay, then in some way, again, I want to introduce in this talk defines a lattice dicing of a certain lattice. Of a certain image in the certain image of the cycles in H1 of the gamma delta prime Z. Okay, then by observing this lattice dicing, we obtain a kind of criterion about the determinacy of the limits of the degenerating prims. It's very interesting because if we start from the random dual graph, we could, random nodal curves, we could not get the unique limits of the degenerating Prim varieties. In some cases, we obtain the unique degenerating Prim varieties, which is just depends on the choice of the double covering, not and independent from the choice of the degenerating families. Okay. And instead of the lattice dicing, we also can identify it as a unimodular system of vectors. Okay, and this notion is also given by the regular matroid. Matroid is a kind of generalization of the notion of basis in just a column space of the matrix. Okay, so it means that we obtain we can observe it by a kind of combinatorics way. Okay, so starting from the graph theory and such a kind of discussion about the combinatoric way, we obtain some result from the regular matroid, and such a result gives the information of the unimodular system of the vectors and even the indeterminacy or determinacy of the degenerating prims. Okay, so by this way we obtain some informations. And in fact, finally, I want to introduce one very important result by Gwena, which says that for a degenerating family of cubic threefolds xt to a cubic threefolds x naught with nodes, okay, such a kind of regular matroid, I mean the unimodular system of vectors associated to xt, it was defined by this paper by ABH, okay, coincides in fact to the system coming from the dependence of nodes on X naught. Okay, so this system coming from the dependence of nodes on X naught is just given by the configuration of the nodes as a place. Okay, so it means that if we have the nodes which sit on just one plane, then such a kind of dependence relation, linear dependency relation gives a unimodular system of the vectors. In such a way, we obtain the system here, and this in fact gives a unimodular system of the vectors defined by the dual graph and the lattice testing. And such an observation finally gives a new result, new proof about the irrationality of the cubic threefolds. So finally, at the end of today's talk, I want to introduce this proof as a corollary. Okay. So this is a plan of today's talk. So do you have any questions? Okay.
Excuse me, sorry. I mean, could you explain a little more about this lattice dicing? I can't.
Yes, again, I want to say, not a precise definition, but I want to say what is a lattice dicing, but it's very easy notion. If we have such a kind of lattice, okay,
Yeah.
then the lattice dicing is given by just a family of the hyperplane which passing through these lattices. So something what this kind of, yes, sections. Okay. So such a family of whole of the plane, hyperplane such as the intersection passing through the lattice is called the lattice dicing. And this lattice dicing is given by starting from the, for example, regular matroid or starting from the dual graph.
I see. And the theorem of Gwena, you mean this degeneration? I mean this, how can I say? This node, I mean the configuration of this node.
Yes, of course, I need to explain more, but the point is that, as I said, regular matroid is a kind of generalization of the columns of the matrix, right?
Yes.
And such a matrix can be given by the configuration of the points. For example, if we have the 2 points on the one line, then it's corresponding to the matrix 1, 0, 0, 1. And they are sit on the same line means that it gives a 1, 1. Okay. So starting from such a kind of matrix, we obtain the matroid and it gives a unimodular system of vectors. Okay. So the point I want to emphasize is that without using this observation about the dual graph, just observing the where is the nodes on the original X node, we obtain the same unimodular system of vectors.
But you mean this dependence of nodes means that several nodes determine other nodes? Or...
no, I mean where they are on the one plane or on the one line, based on so on.
I see. Thank you.
Thank you. Okay, so I want to start the actual talk. Okay, so I want to start from introducing what is a S delta and delta prime, which is associated to a given cubic threefold, okay, or as a even cubic threefold with nodes. Okay. So here, as a general situation, let X be a cubic threefold with finitely many nodes in people. Okay. So starting from nodes. Okay. Then we start from choosing a node x naught. So it means that, as I said, S delta and delta bar, delta prime depends on the choice of these nodes. Okay. Then starting from this nodes, let H be a hyperplane such that x naught, this node is not in this capital H. Okay. And also we take the tangent cone Tx x naught. Okay. So the figure is something like here. Okay, we have the x naught, then the tangent cone Tx x naught. Okay, and then we define a sextic on a quadratic surface S by the intersection of this hyperplane H and the cubic threefold X, and finally tangent cone Tx x0. So inside of all of the X, we have the H intersection X. This is a cubic surface. And with the intersection of this cubic surface with a Tx x naught, we obtain a sextic cup here. So this is a definition of the capital.
Can I ask, is this hyperplane general?
Yes, general hyperplane, but we need a condition that x naught is not on H. For this, we need to choose a node, small x naught.
Okay, thank you.
So this is just a very simple definition of the capital S. But on the other hand, we also can consider the fano variety, or I should say fano surface of X. If it's all lines on X, and in the Grassmannia, we may consider this is a variety or surface. Okay, and as a notation, starting from a point S in this fano variety, I want to denote the associated line as a LS. LS is a line, in fact, inside of the capital X. Okay. Then the theorem by these people gives the birational equivalence between this fano surface and the, in fact, the symmetric product of this sextic. Okay, they are birational. And via this birational equivalence, we obtain the S inside of the, one S appearing in this symmetric product as a kind of place in the fano surface. Precisely, this D naught is given by point S such that x naught is in fact, this line LS.
Excuse me.
Mhm.
So in the previous slide, the S is anyway some curve on cubic or quadratic, may I ask you?
Sextic curve, S is a curve.
Yeah,
Yes.
curve on this quadratic surface or cubic surface, may I ask you?
Quadratic surface. So to draw the figure, I have chosen H intersection X, but the quadratic surface appears when we consider the H intersection the cone Tx x naught.
I'm sorry, why H intersection is not cubic surface?
Oh, no. H intersection Tx x naught is a
I see.
yeah, quadratic surface. Yes. So and finally, by taking the intersection with X, we obtain the sextic.
I see.
Yes.
And in any way, I mean, F is, when I determine this X,
Mhm.
then, this F is given kind of thing.
Yes.
But
yeah.
when I change this H, then, S is, S, so this results tell me that this S is somewhat determined regardless.
Yes, I think, yeah, I need to check in detail, but I think that capital S is isomorphic for any choice of the capital H. So yes, so yeah, there's no problem. And first of all, we take the node. Okay, so it means that S is not unique for capital X. Okay, it depends on the choice of the X node.
I see. I mean,
multiple nodes.
I see.
Mm.
I see. Thank you very much. Thank you.
Thank you for the question. Okay, so the reason why I want to introduce this D node is that to define the delta and delta prime, we need to choose we need to fix a line, and this line should be a kind of good line. Okay, they should be not on the kind of bad place. Okay, so not only the D node, we need to introduce other bad places which is coming from the nodes. But for the case of the multiple nodes, it's a little bit complicated. So instead, I want to consider for the simplicity the case of the X node, capital X has a unique node X node. Okay, but the construction is almost same for even for the multiple nodes case. Okay, so to construct delta and delta prime. Okay, as I said here, I want to assume that X node is a unique node. Okay, then for this case, we consider a kind of bad place F prime and F double prime, which are defined by the situation that when we consider the intersection of the Prym P with the cubic threefold capital X, then usually it is given by cubic curve or the I'm sorry. It should be the cubic curve, but sometimes it can be happen that the intersection is given by just the 3 lines, 2LS plus LT, or the LS plus 2LT. Okay. So we need to avoid such a kind of special case. Okay. And after avoiding these bad places, starting from the choice of the capital F, we can fix a appropriate line L naught. Okay. So for such a kind of fixed line L naught, we can consider the family of 2 planes which contains this line L naught at least. Okay. And let's denote it as N. Okay. Then this delta is defined as a discriminant curve in N for the process of taking the intersection with the original capital X. I mean, delta is a point T in capital N. And if we choose a T, I mean plane in capital N, then since it contains at least 1 line, there is a possibility that another component of the intersection is given by the conic, or conic could be degenerate to just 2 lines. Okay, so here the discriminant curve delta is given by the latter case. I mean the T such that the intersection PT with the cubic threefold is given by 1 line and also the degenerating conic. Okay. By watching the figure, I think you can understand easily. Okay, if we take the point in which is not in discriminant curve, then as an intersection with the PT and X, we obtain the 1 line and the conic KT here. But it can be degenerate when we take the point T in the delta. Okay, we have the 2 line KT. So this is the definition of the delta. And thirdly, the double covering delta prime is given by the point in this fano surface S, such that first of all S should not be the S naught, and also we have the intersection point with this LS with a fixed L naught. So LS intersection L naught is not empty. So it means that in this plane we obtain the L naught LS here. So by mapping such a kind of S to the plane PT, which is spanned by both of the L0 and LS, we obtain a certain element N, which should be in the delta. Okay, so we have a map Q from, so we have defined the delta prime, and finally we have a map Q from the delta prime to delta in this process. And Collino and Murre's result says that, in fact, this delta is a quintic curve with a unique node, which corresponds to the plane containing X node and N node. And more important thing is that delta prime is, in fact, an unramified double cover of delta by Q. Okay, so I want to emphasize again that this is just a construction for the case of the 1 node. So especially about the treatment of the place F and F prime, we need to consider more complicated situation for the multiple nodes case. Okay, so here, because of time, I just want to say that for the case of the multiple nodes, we should change this choice of the L node to more appropriate good line. Okay, So the meaning of the good line is originally defined in Towanda's paper as a condition that all singularity in delta are known and the delta primes are ramified. Okay, but here in the paper, this condition is observed in detail. Okay, in this next section, I want to introduce the Prym variety and the theory of the degeneration of the Prym varieties very briefly. So for this, firstly, let's consider the case of the smooth curve C prime with an involution tau. Okay, no, tau. Okay, then we have the let's assume that starting from this involution, we have the quotient. So let's denote the result of the quotient by C. Okay, so we have the, in fact, the double covering of the C by C prime. Okay, then for such a general situation, we can define the usual Prym variety of the C or C and C prime as a kernel of the norm map from the Picard group of the C prime to Picard group of the C, okay, and takes a component which contains the identity 0. Okay, this is a definition of Prym variety, and we just want to generalize this definition to even the case of the nodal curve. So when C prime has nodes and iota is not identity on any component of the C prime, okay, we define the kind of open generalized Prym variety P naught C prime over C, which is defined by, in terms of the Picard group here, we use the Jacobian of the curves and takes the norm map as before. So the norm map of the from the JC prime to JC and takes a component which contains identity for the card. Okay, but the problem is that it is known that when we define the generalized Prym variety this way, then this is a open variety. Okay, and the reason why this definition of the P naught is appropriate is that, in fact, those Prym varieties are abelian, and similarly, P naught is a semi-abelian. It can be expressed as a kind of extension of the abelian, certain abelian variety capital A. It is, in fact, comes from the H1, the kernel of the H1 of the graph, of the dual graph of the original curve. Okay, and by a certain torus GM. Okay, so P naught is appropriate, but it is open. So the question is whether there is a good compactification of this generalized open Prym variety. Okay, and this is a work, in fact, done by the in the paper ABH.
Excuse me, but why you change this Picard to Jacobian? So this Jacobian means, one cycle on C prime, or?
Yes, because in this case, C prime has nodes. Okay, so honestly, I'm not sure what is happening when we change the J to Picard, but it would be not appropriate because this one is a semi-abelian variety, and it is very good to consider the extension of the abelian variety.
I see.
In fact, this P naught is not related to the, sorry, I want to go back a little bit. The theorem which I have introduced here, okay, because here the Prym variety we are thinking is a normalization, so it is not related to the nodal curve case. Okay, as another approach, here the authors are thinking the generalized Prym variety starting from the nodal curves.
See. Thank you.
Yes, I'm still working for here, so for this part. So because this is a very general theory for the degeneration of the Prim variety. So I think that's a very good question. What is happening if we change J to just a Picard group, and how inappropriate it is an important point. But today I couldn't answer for it. Okay, so as I said, when we consider such a kind of compactification, starting from the degeneration of the curves to nodal curves, there should be a kind of unique limit as a compactification. So unique limiting Prim variety. But in general, it's false for if we start from the general nodal curves. There is a kind of indeterminacy problem. And to express this kind of indeterminacy problem, I need to introduce the lattice testing. Okay, so the lattice testing is given by the following way formally, but this procedure is technical a little bit. So later, I want to introduce just one easy example. Then you can understand how, in fact, we should obtain such a kind of lattice testing. Okay. So the formal definition of the lattice testing is given as follows. Starting from the dual graph delta prime of this nodal curve of the covering C prime, delta C prime. Okay, so dual graph. Okay, firstly, we should take a map which can cancel out as the identity of the involution. Okay, so pi is a map from the homology H1 of this diagram to the H1, so cycles to cycles. But here, the map, this map maps H to the difference of the H and its image by this iota, and takes a formally 1/2. Okay, it means that if we if H is fixed by the iota, then it is cancelled out by this way. Okay? And this image of the pi is a lattice in the image pi tensor R, which is in the space of the all chains of the gamma prime. Okay. Then starting from each edge of this gamma prime, which is there is a, since we are thinking the dual graph, this one-to-one corresponds to each node of the C prime. We obtain the coordinate Zj in C1. Then starting by using this coordinate Zj, we define a coefficient Mj of Zj by the two cases, considering the two cases Mj equal 1 for the Zj can cover all of that Z. I mean, Zj is surjective for this map. Okay, and gives a 2 for the case that image of the pi covers all of the 1/2Z. Okay, and these cases can be translated to the situation that the first case is that the multiplicity of this cycle H is 1, implies that the image also has a multiplicity -1. Okay, and on the other hand, the latter one gives is given by considering the case that multiplicity of the H equal 1, but multiplicity of the tau H equals 0 for some H. Okay, and in other cases, we obtain Zg equals 0. You can see such a kind of translation via this definition. As I said, this is a kind of formal construction, so I recommend you to hear the construction in the example later. Okay. So now we consider any one parameter degeneration family of curves with involution, which in fact degenerate to the nodal curve C0 prime with the involution tau prime, iota prime, iota node. So then the theorem by ABH says that the linear function MJZG in fact defines a lattice dicing HC naught prime C naught of image of the pi, if and only if the Prim variety, if and only if there, in fact, there exists a good compactification P naught C0 prime to C0, and here I want to define it as a generalized Prim variety for the nodal curve, and this is in fact does not depend on the choice of the degenerations. But rather than the lattice dicing perhaps it is more concrete when we consider what is a figure of the original curve. Okay, so the this Prim variety is on the determinacy locus if and only when we consider C0 prime tau is iota is in fact not Friedman-Smith type curve with two end edges. Okay, so this is a very concrete example which is observed by Friedman and Smith, and it is defined by the following four conditions, which says that firstly, the C node is sorry, I should say everything is a prime, but I missed the prime here. Okay, but I hope that you understand what is happening. C node is consisted by two irreduced components C01, C02. And also, when we consider the intersection point, I mean nodes, C01 intersection C02 is given by two endpoints for the case of the two end edges. Okay, and the involution fixed each of the component. And finally, this iota is base point free. Okay. If C0 node is this FS curve, then the Prim variety is indeterminate. One easy example is given as follows. Okay. Please consider the graph delta prime is defined by this kind of figure. Okay. We have the 2 points and 2 vertices and the 4 edges. Okay. And we assume that the involution is given by mapping P1 to P1 prime and P2 to P2 prime. Okay. We obtain such a kind of dual graph. In fact, when we consider two intersecting smooth curves, and the intersection points are given by these 4 nodes. And the involution gives the changes of these two pair of nodes. Okay. Then this dual graph, in fact, satisfies this condition. Okay. So this is a FS curve. So in this case, the compactified Prim variety PRC0 not over C0 is indeterminate. On the other hand, when we consider the graph gamma prime, which is given by such a kind of figure, such as the 4 edges P1, P2, P3, P4 goes to P1 prime, P2 prime, P3 prime, P4 prime by the involution. Okay. Then such a dual graph is given by considering the 3 smooth curves, 1, 2, and finally 3. Okay, intersecting with these 8 points with the involution defined by these arrows, then it gives such a kind of graph. Okay, then this is not a FS curve. Okay, and so it is on the determinate locus. So we obtain the Prim variety of the CL prime over C0. It is uniquely determined. Okay. And for this case, so we can consider what is a lattice testing given by this kind of graph. Okay, so in this case, the way how to get the lattice testing is given as follows. We need to consider the basis of the image of pi, because that image of pi is the image of the homology class H1. I mean the 1 cycles on this graph. Okay, then the basis in this way, in this case, is given by the following 3 cycles. Okay, the 1 cycle is given by first it goes here and then go back here by passing through P1, P2, and with its the difference with its image give one of the element of the image of pi. Okay, so as a letters, it is given by P1 minus P2 minus P1 prime minus P2 prime. Okay. And similarly, passing through this one and takes the image, we obtain as a component. And finally, by passing through the first one and the fourth one, we obtain the third component. Okay. So these 3 elements give the basis of the image of pi. And then we can imagine the dicing by considering the matrix, which can express how many times these points passing through each of the original P1, P2, P3, P4. Okay, so for example, the first cycle corresponding to this first row, first row. Then since this entry passing through P1 first time and P2 second time, but with alternative sign, so cancel out and we obtain 1 here. Okay, and the second cycle will give the second one, the third cycle gives the third one. So the lattice testing should corresponding to the unimodular system coming from this matrix. Okay, so by observing each column of the matrix, we obtain the equation of the lattice testing. In this case, it is given by x equal blah blah, y equal blah blah, z equal blah blah for the integers, and finally x plus y plus z equal blah blah. Okay. By considering all of such a kind of hyperplanes, we obtain the lattice testing. So this is a way how to get the lattice testing. And I think you can feel that there is, in fact, a very strong connection with the matrix coming from the observation of the graphs. Okay. Okay. So here, I think it is a good timing to introduce the matrix. But if there is any question or comment, please ask me now. Okay. So by using 20 minutes, I want to introduce the matroids. Okay. So as I said, the matroid is a notion which is a kind of generalization of a basis of vector spaces. Fixed vector space. Okay. So the formal definition of the matroid is given as follows. Okay. Matroid is starting from the finite set capital E and a certain subset of all of the subsets of E, which is called the independent set. Okay. And if this capital I satisfies the following 3 conditions, it is called the matroid. Okay. The first condition is that empty set is in capital I. And the second condition says that if A is an independent set, and also B is a subset of this independent set, then B also must be the one of the independent set. And thirdly, if we have the 2 independent sets A and B, such that the cardinality of the A is greater than B, then there exists a certain adding entry capital A, small a, such that the union of this A and the original capital B is also the independent set. Okay. But rather than the definition.
Sorry, what is this A on top of A?
The capital A?
Yeah. So in the third point, after the implication sign, what is written there?
There exists a small a.
Exists.
Yes,
okay.
yes, I'm sorry, that was for my notation. This is just there exists. Excuse me.
Okay.
And yeah, rather than this formal definition, again, you can understand what is happening when we consider the following examples. Okay. The first example is, of course, coming from a basis of the vector spaces. Okay. So it is given as follows, starting from a certain capital matrix capital A, and as a finite set capital E, usually imagine that the column vectors of capital A. Okay. Then inside of these column subsets of column vectors of capital A, we can consider all of the linearly independent columns in capital E. Okay. So this is a definition of this capital I. So for example, if we have a matrix given by the identity matrix here with a 1, 1, 1, okay, and it is called M42. And of course, the reason why I want to use this matrix is that this matrix in fact appears in the theory of the degenerations later. Okay, but anyway, as just one example of the matrix. Okay. The column vectors of the capital A is given by all of these columns A, B, C, D, denoted as here. Then any 3 choices of the columns are linearly independent every time. So as a linearly independent columns, we obtain the, sorry, I should say, I'm sorry, this should be maximal I, because we also can choose, of course, just 1 column or 2 column or and so on. So maximal part of this independent set is given by ABC, BCD, ACD, and ABD. So this is a first example. But instead of starting from a matrix, we also can construct the matroid from the graph. So there is a connection between the graph theory and the matrix theory. Okay. So the way how to get the matroid from the graph is given as follows. Okay. So starting from the graph capital Z, as E, in this case, we are thinking, we should think edge set of capital Z, all of the edges. Okay. Then inside of these edges, as a capital I, we consider edges which does not contain any one cycles in capital G. So it means that we can take some choices of the edges, but we cannot take the edges which in fact constructs the cycles. Okay. So let's see just a very naive example. So as a capital Z graph, we take again such a kind of graph which is corresponding to FS curve. Okay. Then we have the 2 point and the 4 edges. Okay. If we choose any 2 of edges here, then always we obtain the one cycles. Okay. It means that as a E, we consider the all of the edge set of the capital Z, but for capital I, again, we just can choose one of the edges appearing here. We cannot take 2 edges, any 2 edges appearing in capital G. So we obtain A, B, C, D. Okay. So in this way, we obtain a certain matroid capital MC. And the good connection of this capital G and this one is that the dual matroid of this matroid MZ can be actually represented by M42. Okay. So here, very precisely, I need to, of course, introduce what is a dual matroid, but roughly speaking, it is given by, for the maximal independent set, we just need to the complement of the each entry from the whole of the capital E. So in this case, in fact, starting from the ABCD as a complement of the ABC, PCD, and so on, we obtain the each of the ABCD. So we obtain the dual matroid in this case. And this can be represented by the column of this matrix M42. So I want to skip this part, but in general, there is a method how to get a representation of such a kind of M star Z, the dual of the matroid associated to graph as a kind of column of matrix. Okay, so such a kind of matroid is called the cographic matroid because dual of the graph matroid. Okay, so here I have introduced the graph matroid and simultaneously cographic matroid. Sorry, graphic matroid and cographic matroid. Okay. And here, I can introduce the connection with the lattice testing. It is given by the definition of the unimodular system of vectors. Okay. When a matroid can be represented by a matrix on R such that all square submatrices are unimodular, okay, then it is called a regular matroid, or the author says that it is a unimodular system of vectors, and I want to denote it as just a USB. And for a given such a kind of unimodular system of vectors, which is represented by generally, since this is unimodular, we can represent by the form as a identity matrix and as a certain matrix capital A here. Okay, so for such a kind of expression INA, we obtain a lattice testing, in fact, of R. Okay. It is given by the way that parallel hyperplanes x dot v equal m for each choices of the integer m for the dicing, and for the choice of the v, which is in the column of the capital A, essentially. Of course, we also should consider the column of the IN for the vertical lines. Okay, but we also have the additional lines from the column of this matrix capital A. So as one example, if we consider the matrix 100111, this is in fact the regular matroid coming from the cographic matroid for the graph, this G, okay, as before. Okay? Then starting from this regular matroid, we can get the dicing by the condition that by considering x and y here and taking the product v, we obtain that x equal m, y equal m, and x plus y equal m, which are corresponding to these 1, 0, 0, 1, 1, 1. So we obtain lattice dicing here in this case. So it means that, again, I want to go back a little bit. Such a kind of other kind of generalization, if we start from the M42, the corresponding lattice dicing is given by the three-dimensional lattice dicing with the one hyperplane x plus y plus z equal m. Okay. Then, very important theorem, which in fact almost gives the idea to prove the irrationality of the general cubic threefold is given by the following observation. So this is just a part of the result in the ABH, but here I just use the result. I just change the statement so that we can use in my talk. Okay. If a Prym variety of a nodal curve C prime to C is isomorphic to a product of Jacobian of nodal curves, then in fact, the lattice dicing HC prime C is a cographic regular matroid. Okay, so here we can reduce the question what is a Prym variety to the observation about the regular matroid. So we can use a kind of graph theory, the result of the graph theory. Okay, and as Murre's proof about the irrationality, it is known that when the Prym variety is in fact the product of the Jacobian curves, then it is rational. Okay, so if such a situation does not happen, then it gives the irrationality problem of the cubic threefold. And in fact, there is a very, very special matroid which is represented by the following matrix, which is denoted as the R10, given by such a kind of very specific matrix. Okay, then I guess that from the graph theory, Oxray shows that R10 is neither graphical nor cographic. Okay, so here, in fact, we can find out the good matroid which gives a contradiction about the theorem. So not a contradiction, how to say, the good counterexample for the setting of this theorem. So what I want to say is that if one finds a degeneration of cubic threefolds such that the unimodular system of the vectors for this Prym variety is R10, it gives an irrationality proof. So I almost want to finish my talk by introduce again the main theorem by Gwena. Okay. We can in fact compute such a kind of the unimodular system H delta 0 prime del 0 by the theorem first I introduced. I want to rephrase again here. For a degenerating family of cubic threefolds xt to a cubic threefolds x naught with nodes, okay, the unimodular system of vectors associated to xt, okay, it is given by, as I said, considering the general theory of the degeneration of the Prym varieties given by the image of the H1s by pi. Okay, then it just coincides to the system coming from the dependence of the nodes on x naught. Okay, so we by checking this one, this is a good way to find where is R10. Okay, as an example, if 4 of the nodes on x naught is on a plane, okay, then such a kind of the linearly dependence condition, their configuration gives a unimodular system. In fact, 4 nodes is on a plane means that we have the independent 3 elements, 3 points, but the fourth one is dependent, so we obtain 1, 1, 1 here. So it can be expressed by the matrix M42. Okay, so starting from this M42, we obtain the unimodular system. On the other hand, we can see that the delta Z prime is 2 quintic and 1 P1 intersecting at 4 points. Of course, to get such a result of the delta 0 prime, we need more observation what is delta, and it was also given by Gwena's paper. Okay. But anyway, via this observation, in fact, we obtain the gamma prime we have observed in the previous example, this figure. Okay, so in this case, we call that by observing the unimodular system corresponding to this graph is given by exactly the lattice testing associated to this matrix. Okay, so the USB is M42. And so finally, in fact, Gwena shows that this unimodular system H del 0 prime del 0 is represented by R10. I mean, the neither is a graphic nor a cographic matroid for the case of the cubic with 10 nodes. Okay, and specifically by considering just a linear combination of these 10 nodes and pencil defined by this central fiber and the smooth ones constructed a degeneration family towards the R10. So it gives another proof for the statement that generic cubic threefold is irrational. Okay. So I mean, essentially, finally, reducing the irrationality problems to the graph theory, we obtain such a kind of result. And the connection is given by the observation of the connection between matroids and the unimodular system. Yes, and and of course, we also need to use the general theorem of the degeneration of Prim varieties. Okay, because of the time here, I want to stop my talk. Thank you so much.
Thank you very much. Is there any question or comment? So may I ask you that why this employing this matroid, I mean, really helps to, I mean, kind of, anyway, you introduced this matroid, or I mean, could you explain a little more what is the role of this matroid?
Yes, matroid is given by finally, essentially finally for the irrationality proof, what we wanted to use is checking that such a kind of unimodular system associated to the degeneration of the Prim variety is given by R10. Okay, so such a kind of appearing of the R10 is the key point of the irrationality proof. But the reason why this R10 is very special is that it is not graphic and cographic. Okay. On the other hand, when we have the situation that Prim variety is a product of the Jacobian, always in such a case, it is given by cographic. Okay. And also, I'm sorry, because of time, I cut here a lot of discussion, but there is a more general theory by the ABH. This explains that, in fact, such a kind of lattice testing has a good information of known more classical degeneration theory of the Jacobian itself. Okay. So it means that the lattice testing can give the connection between the theory of the degeneration of the Jacobian and the theory of the degeneration of the Prim variety. Okay. So via this connection, I think this theorem was proven.
I see. Thank you. But is this, I mean, the matroid should be this R10, or is there any other matroid can replace this R10?
I mean, the matroid.
Anyway, as far as I understand, they construct a certain degeneration which corresponds to this R10. So,
yes.
But is there any other configuration that gives also
in
irrationality?
Gwena's paper, I'm sorry, I do not know whether she or he, but in Gwena's paper, all of the cases of the degeneration of nodal cubic threefolds are observed, starting from the 1 to 10 cases.
1 to 10.
So yes, in any case of the such a kind of multiple nodal cubic threefolds, what is a USV has been determined. Okay, and for each case, case by case, Gwena checks that each of the unimodular system is given by just a configuration of the nodes. Okay. So towards the future work, I think it's very important to say that such a kind of degeneration data is just given by the configuration place of the nodes on X node. Okay. So personally, what I'm interested in is that then what is happening for the higher dimensional case or something like that.
I see. I see.
Can I ask? So can you always degenerate family of cubic threefolds to a cubic threefold with only nodes?
Mm-hmm.
Can there be some always up to nodes? Singular points, or can you get some ugly singularities?
Yes, starting from the smooth cubic threefolds by considering just a pencil given by xt plus tx naught for the any choice of the x naught, we obtain the degeneration family. But I don't know whether we can choose a good x naught such that, for example, such a original xt is sufficiently close to this degenerating point or not. Because yes, another point I have totally skipped is that when we consider the compactified Prim variety, this compactification is based on the theory of the Prym map from the modular space of the genus G curve to the modular space of the abelian variety. So whether in these modular spaces, whether one can fulfill the degenerating point or not is an important point. And in fact, the compactification of the generalized Prim variety I have introduced gives the answer of such a kind of limiting point in the modular space. And it is not given for the general degeneration family, but for the case of the not FS curve case, Friedman Smith case.
Okay.
Thank you for the question.
Okay, is there any other question or comments? Okay, if not, let's thanks to Professor Sasaki again. Yeah.
Thank you very much.
Yeah, thank you.